Hello again and welcome back to my computer vision channel. Today we will be reading the source code for RT DETR, the first transformer-based object detection model to be fast enough for actual practical applications, and the first one to actually beat CNN-based YOLO-like models in this field. So this is the official repository of RT DETR by /RT DETR. So it has two versions, RT DETR v2, and today we take just the v1 version and the PyTorch implementation of it. So if you go to this folder, they have the README file on how to install everything. I'm going to say that compared to all the previous models that I had to deal with, like DETR, deformable DETR, Dino, all of that, this is by far the easiest in the way the code is written and how to install it. So no stuff like custom CUDA kernel. Everything works on CPU, everything works on GPU. You can export it into ONNX if you would like to use it in your project. Nevertheless, I will leave the link to my personal README file on how to do all the installations, just in case it doesn't work out of the box for you following these steps. And the actual training is rather simple as well. So just passing the config that configures all the actual model parameters, and that's it. After you're done with the installation, after you have downloaded the Coco dataset, it's a good idea to actually test that it works. So just run the training and wait until at least the first iteration is done. So yeah, here it is started. So I'm going to interrupt that. So I'm doing all the launches from the repository RTDETR/RTDETR PyTorch folder. And another thing that I do typically is I place little sandbox.ipnb right there, so inside that folder as well. So I'm going to open that Jupyter notebook right now as well. And here it is. So here I have some starter code with basically tools to plot Coco dataset images, annotate classes, bounding box, all of that. And if we look at the actual train script, I'm just going to show how simple that is. So it's just 51 lines of code. Most of that is just adding arguments, and all the logic is hidden inside of this solver. And so this is the object that we'll need to initialize in our notebook as well. So thanks to the fact that I've installed everything, I make sure to launch the Jupyter notebook in the same conda environment in which the installation was done. So after that, I can just copy paste stuff from the train.py function, like including this solver, for example, which imports this class defined in the repository, and I can use it. And so I basically copy the code from train.py. So I initialize the config, initialize the solver, and everything else important is hidden inside this solver. So these are the couple of commands that you need to call to actually initialize it, to load the data set and prepare for training the model. And we can access that data from the solver itself. So if we do solver.trainDataloader.dataset, we get the dataset, we can get train data loader, we can get validation data loader, and so on. And typically I like to actually take a look at what sort of images we get, right? So this is the image number 0 from the Coco dataset. We've seen that quite a few times in my previous video, because this is the image number 0. So we can see like actual objects, we can see class annotations on top of that objects, and so on. Another thing that we can do is we can keep executing the same cell over and over. So that causes the dataset to fetch image with the same index, but apply the transformations with a different seed. And this is how you get a sense of what sort of data augmentations are used, right? So sometimes you'd see that the image is shrunk and the majority of the image is replaced with this black padding. Sometimes you'd see that it's stretched, and so on and so forth. So this gives you some idea about how what sort of image augmentation techniques are used. and they are all actually printed right here in the dataset class. So you can see random zoom out, random IAU crop, horizontal flip, resize, and so on and so forth. So not that many augmentations. One thing noticeable compared to other models is that we always resize to the same size. So we don't really pass variable size images to our transformer. This is how we can get the actual example from the data loader. So we just perform exactly one iteration over it. We get out the batch, which is now an object that contains images and targets. And the first element in the batch is images, second element in the batch is targets, and the batch itself is 4 by 3 by 640 by 640. So all the images are going to be this 600 by 600 resolution. We have 3 color channels, and the batch dimension is 4. And that is again the example of an image from the trained data loader now. So since during just fetching the image from the dataset, we already resize them to the same size, we don't really need to think about padding and masking and all that stuff that usually comes up if you try to unite variable sized images in a batch. Here they are all of the same size, so this is quite simple, and this is how we can get the actual model out of this solver and just apply it. So this call calls inference on images and targets, and I can just execute that and get out some predictions. We can check what the output of the model is. So we go pred logits.shape. So we have 4 by 300 by 80. So for each of the 4 images in the batch, we got outputs for 300 queries, the same number of queries as in Dino. And for each query, we get 80 class predictions for 79 Coco classes and special no object class. We can go for predicted bounding boxes. Then we, instead of 80 predictions per query, we get 4 predictions per query for bounding box coordinates. We can look at what other outputs there are. So for example, there are denoising aux outputs, right? And that's actually a list of length 6. So for every layer in the decoder, we get these aux outputs for denoising, and let's take one such example. And so apart from 300 normal queries that are actually used during inference, we also have 200 denoising queries that solve their special denoising objective. So we have that is pretty similar to Dino. Next, let's print out like what the actual class for the model is, and let's see how it looks like. So the class of this is RT DETR. Let me find that in the code. And again, this is pretty short, right? Just look at this. So this is the forward method, and it's just 10 lines of code. What? You could do that all alone, and you didn't, right? So you have backbone, encoder, decoder, and that's what you return. So I'll break at the very beginning of the forward call, and to get here, I go back to the cell and press debug cell. So x, what is x? X is a tensor of shape, the same one we've seen before, so 4 by 3 by 600 by 600. We see some code here regarding the multiscale, which says that we actually want to train our model on different sizes. So as we've seen in the data loader transforms, all the images will actually be 640 by 640. But to give the detector more range in the sort of images you can use it for during inference, we apply this bilinear interpolation randomly on each batch to train detector on different image sizes. So this is useful if someone, for example, wants to put this model on a robot with lower resolution camera, and the picture sizes will be different. So doing this during training gives us more adaptability to different picture resolutions. So then we call the backbone, and the output of the backbone is a list of length 3, and so all the shapes I can print like this. So again, batch dimension is 4, and I get one image 84 by 84 with 512 embedding dimension. Then the next one twice smaller, so 42 by 42 with 1024 dimension embedding, and the next one even smaller, 21 by 21, but now with the biggest embedding. So this is typical for backbone outputs. Basically this one is the actual output of the backbone, but we also return a couple of intermediate images to have this high resolution semi-processed image that helps us for precise bounding boxes. So next let's see what the encoder type is. So it's hybrid encoder. Let's find that in code. So here it is. It inherits from an Android module. So we look for the forward pass, and here it is. And let's just continue here. And again, we just see that we have features of length 3. So we get these 3 feature levels passed in. Then we apply these input projectors. So let's just print out what that is. And that's a bunch of 2D convolutions. Kernel size 1, stride 1, which means that basically we project every pixel independently, not looking at neighboring pixels. And we project all of the 3 levels with different embedding dimensions down to a single 256 embedding dimension. And we also apply batch normalization. So then we have this for loop. Self-use encoder IDX is just a list of length 1 with a number 2 in it, which means that we're going to apply the actual self-attention only to the last level, only to the lowest resolution 21 by 21 image. So now we do the typical thing for DETR-like models. We flatten it out. Let's see what the shape of this is. So it's now 4 by 441 by 256. So we flatten the 21 by 21 image. That's where we get this 441 from. And we still have 256 embedding dimension and 4 batch dimension. Then we have this built 2D sine cosine position embedding, again quite typical, and then we apply the actual encoder. Let me just quickly show how encoder looks like. So the type of the encoder is module list. So it consists of a bunch of okay, so it starts with this transformer encoder class. Let's find it. Here it is. So transformer encoder has a bunch of layers. So it applies them one by one. And then transformer encoder layer, right? So here it is. This is your typical multi-head self-attention. Right, so you have source. We'll not debug through that because it's so similar to what we've seen before. So we add position embedding, right? This is just the sum operation. We perform self-attention. Self-attention is pytorch.nn.multihead attention, so a classical pairwise self-attention. Then we get residual, normalization, feed forward, and return, right? So this is the most classical transformer self-attention layer, the same as in DETR, so no deformable attention here, nothing fancy, just the typical stuff. So let me close this for now and come back to where we were. So let me just continue through this and print out the shapes of the result. So the shape is the same as the input, so it's basically this flattened 21 by 21 image. and then we can return it to reshape it to the original size, right? So this projfits object now contains the encoder output, and the shape of that has returned. Sorry, so this projfits is length 3, so we still get these backbone outputs, and encoder index is 2, right? So the output of self-attention layer is in there with index 2, right? And that is now unflattened 21 by 21 image. So this was the what is called interaction part, where we actually apply the attention, where we actually allow pixels within this 21 by 21 image to communicate to each other. And next we do what is called feature fusion. So let me come back to the slide for a little bit. So this is how feature fusion needs to be done in RT DETR. So we have backbone outputs, the lowest resolution of which 21 by 21 was just passed through the self-attention layer, and then we do fusion. So we allow this 21 by 21 and 42 by 42 images to fuse together to propagate this precise pixel information to each other. Then we go up again to get this 84 by 84 image, and then we go down, back down to 44 by 42 by 42, and then 21 by 21 again. So let's try to see that in code. So after the encoder self-attention, we now have these two for loops. So the first one performs upsampling when you go from 21 to 42 to 84, and then the one that does downsampling, now 84 to 42 to 21. So this arrange loop here, let's just print out the result of that. It'll have two iterations. So we have feature high, which takes in these inner outs. So inner outs is like a result of the first upsampling branch of this S shape that we've just seen on the slide, and then the actual outs would be the encoder results. So we start by putting the last element in this proj feeds into inner outs, and that's our 21 by 21 image that just got passed through self-attention. So it's quite confusingly called feature high here, despite the fact that it's actually the smallest resolution, probably because it refers to the depth of semanticity, not the actual pixel resolution here. And feature low is the next level. So feature low is going to be this 42 by 42 feature map. So first we actually apply one extra convolution to this 21 by 21 image. So just to be sure, so this one doesn't change the shape. So it's 256 to 256, kernel size 1, stride 1, and we put the result of that back into our output. So we just basically apply one extra convolution to every level that we have here. Next we upsample, so this f.interpolate is basically bilinear interpolation, or in this case it's actually not bilinear, it's nearest neighbor interpolation, but it still works pretty much the same. So the result of that is the same as if you just drag and zoom in or out on the image on your computer. So we can see the shape of this now, and it's 42 by 42. So we just zoomed in, increased the size of our image from 21 by 21 to 42 by 42, and then we apply our FPN blocks. So FPN block is of type CSP rep layer, so that let's go to that. Here it is. Let's break in the forward method and continue. So the X shape is 42 by 42. Sorry, I've missed some places. Right, so we apply that to the concatenation of one 42 by 42 image that we've got from this upsampling and another which is just the backbone output, and we concat them together on the dimension 1, so on the embedding dimension. So what we get from here is 42 by 42 picture, but now with twice the embedding dimension. And so this is what we do now. So we apply the first convolution, And you can already see how feature fusion is happening here. So this convolution is kernel size 1 by 1. So we're not looking at neighboring pixels here, but instead we take each pixel and project 512 dimension embedding down to 256 using basically a fully connected layer. Which means by this point, we had two embeddings concatenated together here. We projected that down to one embedding, which is already this sort of merged version of the two. So we exchange the information between them. So then we have this bottlenecks block, which is now this RepVGG. So RepVGG can be seen as an analog of basically one ResNet layer, but they use, so it's basically a convolutional neural network. As you can see from here, they have a bunch of convolutions that don't change the embedding dimension. Some of them are 1 by 1, some of them are 3 by 3. They don't change the shape of the output. And it's the same as one ResNet layer, but this particular block there's a paper about that called RepVGG, which talks about the so-called structural reparameterization, which is basically saying that, in ResNet layer, we have these two types of convolutions, so 1 by 1 convolutions, the 3 by 3 convolution, and we apply them together, and that's how the ResNet sort of works. But that's slow because we have this branching in the compute graph. And so what they do is they basically do the same during training and then just convert that to something simpler, to a single convolution, using just pure magic of math. So the result is the same, but the actual inference speed is faster. So that's an interesting thingy, but for us it basically means that that's just a convolutional layer. So after these bottlenecks, we have this second convolution, which is again kernel size 1. Again, this projecting down. So it's applied to initial x. So this is like a little skip connection that applies directly to x. And then convolution 3 is the identity, so it's not doing anything. So here is the slide representation of what just happened. So we have this 20 by 20 image, we have this 40 by 40 image. We enlarge, upsample this small image. Then we concatenate along the embedding dimension. And then we apply basically two branches, one branch that performs fusion by just applying one-to-one convolution, taking this 512 concatenated embedding and merging that into a single embedding. And the second branch that does pretty much the same, but also has this extra RepVGG block that performs some more calculations. And the result of that is this single one 256 by 40 by 40 image. So it's the same shape as we've seen the bigger image from the input, but it now contains fused information from both of these images. And so let me just continue and point out the shape of the result. So now inner out shape is again 42 by 42 by 256. So we've back to the same shape as we had for feature low, but now it's fused together. And we put that result on the first position of our inner out. And then on the next iteration of the loop, we basically do the same thing, but now with 42 by 42 image and 84 by 84 image. So we upscale that another level up. And that's the end of this for loop. And then the second loop is pretty similar. So now we have this feature low, feature high again. Let's print out the shapes of these. So feature low is now 84 by 84. Feature high is 42 by 42. And now we go downwards. So we, instead of upsampling, we do downsampling, right? So downsampling is done slightly differently. It's done using just a convolution of kernel size 3 and stride 2. So we basically, this means that we apply the convolution and shift it a bit more than we had to, thus pretty much skipping every second pixel. And so this downsampled version of the feature is now going to be twice smaller, so 42 by 42. And then instead of these FPN blocks, which consisted of RepVGG, we now have these pan blocks. Pan block is again CSP rep layer, again RepVGG. So this one is actually exactly the same. So the same sort of fusion thingy happening, and we concatenate the output, right? So if we now continue to the very end of the encoder and just print the shapes. So it is the same as we would have in deformable data, for example. So 3 levels, 84 by 84, 42 by 42, 21 by 21, but we've only applied convolutions to these higher resolution images, which saved us a lot of compute. Next we have our decoder. So let's bring the type of that. It's RT DETR transformer, so let's find it. Here it is, RT DETR transformer forward method. So let me just break at the very beginning of it and see what's going on. So just to confirm, the feeds here now refers to the output of the encoder, also sometimes called memory. Then we have this get encoder input call, which basically iterates over the 3 levels that we got, applies this input projection. Let's just see what it is. That's pretty simple, just 1v1 convolution, not changing shapes, and then flattens everything out. So out of that we'll get the flattened sequence that we can use in the decoder, as well as the actual shapes and indices where each level used to start. So I'll just continue through here. The memory shape is 4 by 9K by 256. So there's 9261 that comes from basically 42 by 42 plus 21 by 21 plus 84 by 84. So we get these 3 levels that we got from backbone, from encoder output, flatten them all together, and we've got our huge 9K sequence of elements. We have these denoising extra queries as well. So this part will not read too deep in, but that's basically exactly the same as in Dino. So apart from 300 normal queries that try to detect objects on the image, that participate in the Hungarian matching loss, we also have these denoising queries that have their own thing and basically just connect it to the ground truth object, skipping all the matching parts, skipping the Hungarian matching loss, and that is more direct, that is more stable, and that helps train the decoder, and then during inference you just don't have this part. Then we have this get decoder input function call that sets up the actual queries. So this is the one we're interested in to see how query selection is done. So first of all, we have this things called anchors here. Let's just take a look at what that is. So it's 1 by sequence length by 4. So for every element in the sequence we get 4 bounding box coordinates for the anchor. And let's print out all of them for 10 points, for example, and we can see how they look like. So don't get scared. These are not the same anchors as in YOLO, for example. So they are used just to convert the relative prediction that we get from every pixel to absolute prediction that actually participates in the loss. So the anchor themselves do not participate in matching, so they don't really affect that much the sort of the way the model is trained. They're here just for number conversion, basically. Then we have our memory, and where every sequence element in the memory corresponds to a pixel in one of the feature levels that we had, one of the 3. And then we apply some projections to get out the encoder class and bounding box predictions. So you have this enc output, enc score head, enc bounding box head. All of these are just basically linear layers and 1v1 convolutions. Oh, this one is also linear. So this encoder output is basically projects 256 to 256, just one projection, nothing much going on. Then we project that 256 down to 80 to get our 80 class predictions. And then for bounding box, we get 256 to 256, and then down to 4 bounding box coordinates. And then we select the top k. So we select top k by the predicted class probability, whatever that means. And what is happening here is now exactly the same as it was in Dino, right? So the model predicts some probability, and that's what we use to select queries for the decoder. But as we'll see later when we take a look at the loss, the actual meaning behind that number is different. So apart from class prediction, it also encodes the confidence in the bounding boxes that we have just created. So then, as we'll see later, we will use deformable attention in the decoder. So for deformable attention, we also need reference points, which are basically the centers of attention for deformable attention. And we get them from just this top k encoder output coordinates. So we've selected some sequence elements, and from every sequence element we can get the actual embedding, we can get the confidence scores, class predictions, and we can get the actual bounding boxes. So out of the bounding boxes we create the reference points, right? So every pixel detected some sort of object, and we take the center of that object as the center of attention, and we also get the target, which are basically queries, as this embedding of the pixel, and this is what we return. So after this get decoder input function, we call the actual decoder. I will not read too deep into that, but just show you what it has. So transformer decoder. Again, it iterates over the layers, so it has these reference points that are getting updated from layer to layer every time it calls the transformer decoder layer. So this thing uses self-attention as just pytorch.nn.multi-head attention, so full pairwise attention. It also has this MS deformable attention for cross attention. So self-attention is query to query, so 300 to 300, not that much. For cross attention we have 300 to 9k, and that's quite a lot. So here we opted in to do deformable attention. The actual implementation of deformable attention is rather simple as well, because by now we have the implementation of the actual deformable indexing into the tensor with bilinear interpolation as part of the actual PyTorch. So the core function here, so we have the forward method. So again, not reading too deep into that, this is the same as in Dino, this is the same as in deformable DETR, but basically instead of doing full pairwise, we first take a look at the query, use the query itself, project it down to select which pixels, which sampling offsets we need, and from there and reference points we select the actual pixel indices. Then we do this MS deformable attention core function. And this one uses pytorch.f.gridSample. So gridSample is this operation that used to need a custom CUDA kernel that basically takes in a tensor of values, another tensor of indices, but now the indices are not integer, they are floating point numbers that can basically be in between the pixels in the value, and so we need to apply bilinear interpolation to select the actual values. And here it's already implemented in PyTorch, so we don't need anything special to use it. Coming back up to the decoder layer, so you have this MS deformable attention for cross attention. Other than that, everything is pretty similar to how it was in previous DETR models. So we have query key and value. we apply self-attention, some dropouts, normalization. We apply cross-attention, some dropouts, normalization. We apply feed-forward network, and again, some dropouts, residual connections, and that's it. So all of that is exactly the same as in Dino. Next, let's just quickly look at the actual shapes of input and output of the decoder. So here is the decoder call. So the target is basically the same as query, right? And it's of the sequence length 482, which is 300 queries for just the normal decoder, and then 182 special denoising query. And then the memory shape is 4 by 9K, this encoder output sequence length times 256. And then out of that we get output bounding boxes and logits, which are of the same sequence length of 482, but down here we can see that they get separated, so we put normal 300 queries that will be participating in the Hungarian matching loss into one key under the dictionary, and the denoising queries by another key. And we can see here that the 300 normal queries and 182 denoising queries. And this is what is returned from the model. So this is the decoder, and then in the RT DETR, result of the decoder is just returned from the model. So we can break out of here and take a look at the final piece, which is the loss. So we can get the loss by going for solver.criterion, right? And to actually call it, what we need to do is we need to pass in predictions of the model to the criterion and the actual targets from the batch that we got out of Dataloader, right? So let's take a look at what that is first, right? So it's a set criterion. Here it is. This one again looks typical to DETR. So down here we'll have the forward method. The forward method gets in the outputs, which have outputs for all the intermediate layers, the predictions, the bounding boxes, labels, all the denoising objective predictions, and so on and so forth. Then it calls self.matcher. So self.matcher is the thing that does Hungarian matching and actually decides which of the ground truth objects will get matched to which queries. And then we just iterate over all the primary final outputs of the model and over all the auxiliary outputs, the intermediate layer predictions, and just compute the loss using the same function. So I'll put the breakpoint somewhere here right before the matcher, and then actually debug into this cell with criterion call. So again, as outputs we get everything that we got out of the model. As targets we get everything we know about the images themselves. So for example, outputs, pred logits, shape, that's 4 by 300 by 80, right? The first thing we do is we separate out every aux output. So if we print out like what are the keys of what we got from the model, we get pred logits, pred boxes, aux outputs, that's and DN aux outputs. So pred logits and pred boxes are predictions from the last layer. Aux outputs are predictions for all the intermediate layers, and they will participate in the loss. And then DN aux outputs are predictions of these auxiliary denoising queries. They will also participate in the loss, but only the first two will participate in the matching. So we call the matcher, and let's see, for example, targets, boxes, targets 0, boxes, shape. So this will give us the number of objects on the first image. So the first image currently being processed looks like this. So we have 12 phases, basically, called remote here for some reason. That's probably my mistake with the classes initialization. Nevertheless, so we call these matcher, and the goal of this matcher is to take the 300 query outputs, compare them to these 12 ground truth objects, and come up with the matching rule that matches the best predictions to these objects. So we'll not read into that, but just print out the result. So it's again a list, and the first element of that is a tuple, and the first element of that is a tensor, and the shape of that is 12, right? So we get exactly 12 matches, and these first element in the tuple basically says the indices of those model output queries that got matched, and the second element in the tuple tells us to which ground truth objects they matched. And we also compute the number of boxes, which is basically sum of the ground truth objects of all the stuff we have in the batch. So for 4 images, we get 31 boxes in total. And then we'll call this getLoss function for every loss that we have. So let's break somewhere here and see what loss we actually got. So the loss here is VFL, and that is the function corresponding to it. So I break in the beginning of that. Again, outputs for now is everything we've had, targets for now is everything we've had, and we also have these indices that tell us how they actually match. Then what this call basically does is we now get this flat list of IDX. So IDX 0.shape, that's 31. So we basically flattened indices from all the 4 images into one object, and we'll do the same for predicted bounding boxes and target bounding boxes now. So this shape is now 31 by 4, and this shape is 31 by 4. So we basically use it to compute loss for all the images at once. So the next thing we do is we compute the IUU between these. So IUUs is now the object of shape 31 by 31, where we now know the intersection between each such object, right? We get out the actual classification predictions, something that should indicate confidence, and in what exact way we'll see right now, because the meaning behind this confidence prediction will be determined by what loss we have. So for now, we just basically get that out of the model, reshape it to the same shape as we need. So for example, this target here, we get from targets, and that's basically the actual vector of class indices. And then this one is one hot. So we expand that into one hot encoded vector with dimension 80. Let's look at the shape. That's 4 by 300 by 80. Right, so we expanded that into the number of queries, we expanded that into the number of classes that we have. So we have the target, we have target score O, and target score O is now the IUU that we've calculated between that ground truth object and that predicted object. And this shape of that is 4 by 300, right? So for every query, we now know which IUU it has between that and the ground truth object. And let's print the actual values for that for the first image. So for the first image, most of them are zeros, and then some of them actually have some intersection. And remember, our goal here is to predict some sort of confidence that is a combination of confidence in the class, which is just given by the class probability prediction, and confidence in the bounding box. And this IU, the better it is, the higher it is, the better we have predicted the bounding box. And you can see that the target score, the final thing that will feed into the loss, is now multiplication of this target score O, the IUs, with target, the actual one hot encoded target labels. So again, let's print the shapes. And let's print the target for, I don't know, let's get image number 0, and then first 10 objects, Okay, everything is 0 here. Let's take the second 10 objects. Right, so the query is 20 to 30. You can see that we have some ones here, for example, right? So query number 22 is detecting some object here, right? So this one is 1, right? And now if we get the same for target score, so target score 0, 20 to 30, right? So now query number 22, instead of 1 here, we get something that is much smaller than 1, 0.15, because even though we have this correct one-hot encoded label, the actual IU between that and our prediction is quite small, so the confidence is also smaller. So this is what happens in this special uncertainty minimal query selection. So then we have this actual weight, which basically turns it from a cross-entropy loss to focal loss, and then we compute the actual loss. So we get as auxiliary digits, target score, which is this multiplication of IU and class labels and the weight. So this is like the most interesting loss that differs in RT DETR compared to Dino. So once again, this line is probably the most important in RT DETR loss. So we multiply the target, the actual one-hot encoded labels, with target score O, the actual IU or our confidence in how good we predicted the bounding boxes, and from that we get better query selection and slightly different loss as well. But obviously, apart from these, we'll also have loss that takes the actual bounding boxes into account, and we can see that here we have L1 loss, generalized box IU, and this is pretty much it. So this was it for today. Hope that answered some questions, hope that was useful. Hope to see you soon.